So the plan for today is we are going to wrap up the discussion of neutrino matter effects from the day before yesterday. And then I would like to talk for the rest of the lecture about sterile neutrinos, first in a terrestrial context and then about sterile neutrinos as a dark matter candidate. So regarding neutrino matter effects, remember we had last time we had talked about processes like this where a neutrino scatters off an electron from the background matter, but without exchanging any momentum, so coherent forward scattering. And we had argued that because in this type of process it's impossible to tell exactly which of the many electrons in the background the neutrino has interacted with, we need to sum coherently over all possibilities. So that leads to an enhancement factor given by the electron number density, and that makes this process relevant, even though it's of course suppressed by a Fermi constant. And then we have calculated the effect on the neutrino Hamiltonian or Lagrangian by essentially treating the electrons as a background field and taking the expectation value in that background. And we've seen that the term we get out looks exactly like a potential, a flavor-dependent potential affecting neutrino oscillations. And we've then plugged this potential into the neutrino oscillation phase. So this phase, which is given by P dot L, where P is the momentum operator. And then if we express this in terms of the energy, so the energy is given by the Hamiltonian minus the potential, because we want only the kinetic energy, minus the mass matrix squared. So these are at this point still operators. We can work in whichever basis we want. The important thing is that V is diagonal in the flavor basis but off diagonal in the mass basis. I'm not going to do this calculation explicitly because that's part of the exercise sheets. I'm just going to give you the final result and discuss it. And this final result is that this matrix, it's going to have the following eigenvalues. So if I express this in terms of, I'm writing them in the same way as I've written the eigenvalues of the unperturbed Hamiltonian, so the vacuum Hamiltonian. So in the vacuum Hamiltonian, the eigenvalues are of the form delta m square over 2e times, times L. I'm omitting that factor of L here. So I'm effectively defining now a delta m effective squared. So that's essentially a parameterization for how the eigenvalues of this momentum operator change in medium. And the result is square root 2 G Fermi NE minus delta m square over 2e times cosine 2 theta square plus delta m square over 2e squared times sine square 2 theta. So the first thing you can see from this expression is if the matter density is set to 0, then this reduces just to delta m square over 2e, because cosine square plus sine square gives 1. One can then take the square root and ends up with just delta m square over 2e. So just as a sanity check, this shows that we recover the expected vacuum result. We also see that if the background matter density is large, then this term will be entirely dominant. So in that case, there's hardly any sensitivity to the fundamental vacuum value of delta m squared, and everything will be dominated by the matter potential. We can also similarly define an effective mixing angle, sine squared 2 theta effective. And that is given by No, let's write down just sine 2 theta effective, not sine square. So this is sine 2 theta times delta m square over 2e divided by exactly the same square root again. So square root 2 g Fermi ne minus delta m square over 2e times cos 2 theta parentheses squared plus delta m square over 2e square sine square 2 theta. So once again, the sanity check is that in the case of vanishing matter density, this reduces to just sine times 2 theta. The square root, as before, gives delta m square over 2e, which cancels against the delta m square 2e in the numerator, so all you're left with is sine 2 theta. In the opposite limit of very large matter density, the square root is again dominated by the matter potential. And this means that the term here in the denominator becomes much larger than the term in the numerator. So what that means is that in the case of large matter density, mixing is very strongly suppressed. So let's write this down. So for Ne equals 0, we recover delta m effective square equals delta m square and theta effective equals theta, the vacuum angle. So for very large Ne, theta effective tends to 0. And that's not too surprising, because if you look at the structure of this Hamiltonian, in the case of large matter potential, this V operator dominates over everything else. And the V operator is diagonal in the flavor basis. So if that is the dominant term, then this means that the whole momentum operator is diagonal in the flavor basis, and that means that essentially mass eigenstates and flavor eigenstates get aligned with each other. Okay, and now perhaps the most interesting case is the case where this term here in the first parentheses is 0. So for square root 2 g Fermi Ne is equal to delta m square over 2e times cosine 2 theta. So in this case, the first term here goes to 0. The second term, we can take the square root, and we see that in this case, the second term here, it's exactly identical to the term in the numerator. So it cancels. So that means that sine 2 theta effective goes to 1. In other words, in this case, if this condition is satisfied, the mixing becomes maximal, no matter what the mixing is in vacuum. So theta effective becomes maximal, which means pi over 4, independent of the vacuum mixing angle. Independent of theta. So in other words, we have a resonance. For one particular neutrino energy, mixing becomes maximal no matter what it is in vacuum. And this is what's called the Mikheyev-Smirnov-Wolfenstein or MSW resonance. Of course, it only happens at one particular neutrino energy, and you can see if you look at the structure of this equation, you see that if you compare this to the usual form of a resonance condition like a Breit-Wigner form, then you see that the width of the resonance is given by the second term here. So this means the vacuum mixing angle does have an effect in the end, namely an effect on the width of the resonance. So for small vacuum mixing angle, the width of the resonance becomes very small, so it affects only a very narrow range of neutrino energies. Now, if you imagine you have a neutrino flux with a broad spectrum, then this means that overall the impact of the resonance becomes smaller. But if you have really monochromatic neutrinos, then you can have results that are dramatically different in matter from vacuum. And so this resonance behavior, this has rather dramatic phenomenological consequences. First of all, it means that at a certain energy, neutrino oscillations are strongly enhanced. For the resonance driven by delta M31 square in the full 3 flavor picture, this happens at energies of a few GeV, so just above the energy of a typical accelerator-based neutrino experiment. But those experiments can still see the rising tail of the resonance. What's even more important is something that I won't go into detail on here, but it's also on the exercise sheet. And this is what happens when neutrinos travel through matter of slowly varying density. If neutrinos travel through matter of slowly varying density, then, so that happens for instance when solar neutrinos travel out of the sun, then what they experience is that the effective mixing angle slowly changes. And that means the neutrinos are kind of keeping track of the mixing angle. So they are converting adiabatically. So for instance, at the center of the sun, you start with a situation where the mixing angle is 0. Basically, at the center of the sun, the electroneutrino is aligned with the nu2 mass eigenstate. So the neutrinos you produce are essentially in the nu2 eigenstate. Then, as they move out of the sun, the mixing angle slowly changes, but because all of this is happening adiabatically, they effectively stay in the nu2 state, even though the relation of that state to the flavor eigenstate changes. So that means by the time they get out, the state that they are in, namely nu2, is now no longer a pure nu-e as it was at the center, but it's a mixture of nu-e, nu-mu, nu-tau. And that's exactly why solar neutrinos disappear. So I'm just going to write down a short comment on these consequences. So consequences, long baseline oscillations enhanced at specific energy. Or let's say in a specific energy range, because for the parameters in the standard model, the resonance is relatively broad. In a specific energy range. And the second effect is that for slowly varying NE, for instance in the sun, we have this adiabatic flavor conversion. And for that, see the exercises. So the way you demonstrate, you calculate this adiabatic flavor conversion is you write down the Schrödinger equation for the neutrino state. So there is the time derivative of the two-dimensional flavor vector, which has nu-e in the upper component, nu-mu in the lower component. That's the left-hand side. The right-hand side is the Hamiltonian. But now when you do the transformation from the flavor basis to the energy basis, then you need to take into account that not only, well, the wave function has a time dependence, but also the mixing matrix has a time dependence. So you get these extra time-dependent terms. And then you argue that for adiabatic flavor conversion, this time dependence is slow, so you drop them from the equation. And then you will see that the neutrino stays essentially in the same energy eigenstate, even though the relation between that energy eigenstate and the flavor eigenstate changes along the trajectory. And then the conclusion is then basically if you produce the neutrino as, say, a nu2, it stays in a nu2. But the meaning of what a nu2 is in terms of flavor eigenstates changes, and therefore it's no longer a pure flavor eigenstate as it exits the sun. Okay. That's it for wrapping up the MSW effect. Do you still have questions on neutrino oscillations, meta-resonances, and so on? Yeah?
I maybe didn't understand why in the center of the sun it is specifically a nu2 eigenstate.
You can't see that directly from this equation because here I have only sine 2 theta effective, so theta equals 0 and theta equal pi over 2 is equivalent. So theta effective equals 0 would mean nu e equals nu 1. Theta effective equal to pi over 2 would mean nu e equals nu 2. You can't see that from this equation. For this, what I should have done is I should have written this down not in terms of sine 2 theta effective, but in terms of tangent theta, which is in principle what you get from the diagonalization. So in a sense, I've thrown away that piece of information here. So that's why you can't see. But if I were to write this down in terms of tangent theta, then you would see that remember a tangent, so if this is theta, then tangent theta behaves something like this. It has the singularity here at pi over 2, and then you would see that tangent theta is actually approaching infinity, not 0, and that is an indication that it's pi over 2. Okay. Now the plan for the rest of the lecture is I would like to talk a little bit about so-called sterile neutrinos. So this moves us away from the standard model and into the realm of physics beyond the standard model, and in particular towards the possibility that there are more than 3 neutrino flavors. And I first want to show you some slides on this about the experimental situation, and I will also use this opportunity to touch upon another topic, namely neutrino-nucleus interactions, but we'll see how we get there. So let me switch on the projector again. Dun. You see, is it waking up? It should be on. Yes. Ah. Okay. Right, so sterile neutrinos. What do I mean by a sterile neutrino? When we talk about sterile neutrinos, it means that we are assuming that the neutrinos mix with a state that is also a neutral fermion, but does not belong to any of the standard model families. In particular, this extra neutrino state would not be allowed to couple to the W and Z bosons, because if it did, then unless it's super heavy, we would already have seen it. So in other words, the sterile neutrino is essentially the equivalent of what we previously called a right-handed neutrino. In a sense, the term right-handed neutrino can be a bit misleading because every chiral fermion comes with a left-handed component and a right-handed component. And which of these we call the particle and which of these we call the antiparticle is completely arbitrary. So let's in general call this particle N the sterile neutrino. In the literature, it's sometimes called sterile neutrino, sometimes right-handed neutrino, sometimes heavy neutral lepton, but that's all exactly the same thing. And then any such particle can couple to the standard model through this operator. That's the Yukawa coupling of the neutrinos that we've already encountered when we wrote down Dirac mass terms. You have here on the left-hand side, on the left of the operator, you have the standard model lepton doublets, then you have the Higgs field, the Higgs doublet, and you have the sterile neutrino field. And one reason that operator is interesting, because it's the only renormalizable operator in the standard model through which the standard model can talk to a singlet fermion. So if we believe that there's some sort of dark sector in particle physics, because we know we need a dark matter candidate, and there isn't that many ways how such a decoupled sector that is uncharged under the standard model symmetries can talk to the standard model. And this is one way it can. And in fact, for a singlet fermion, so for a dark sector fermion, that's the only way. The other possibilities are, for instance, the Higgs portal for scalars or the U1 mixing Moore portal for gauge bosons, like dark photons. So, why is this interesting? First of all, sterile neutrinos are a very minimal extension of the standard model, so you can in principle add them to any model that you like. They usually don't cause much harm. At the more top-down, from a more top-down perspective, they could be leftovers, for instance, from extended gauge multiplets. Imagine you have some grand unified theory, you sort your standard model fermions into the multiplets of that symmetry, then sometimes these multiplets have extra components that do not correspond to standard model particles, but to states that are charged under the full gut group, but uncharged under the low energy symmetries that we observe. So these particles would then manifest as sterile neutrinos. And in fact, as we've already seen, sterile neutrinos do have useful phenomenological applications. For instance, they can explain neutrino masses in the context of the seesaw mechanism. They can explain, we've not talked about that, they can explain the cosmic baryon asymmetry through a process called leptogenesis, and I assume that Sheda Ipek during the third week of the school will probably touch upon that in her lectures on baryogenesis. They can explain the dark matter. We're going to talk about that towards the end of this lecture. Well, they can act as a mediator to the dark sector. I've already argued that they are one of the few portals to a singlet sector. And finally, for a while, they were quite popular for explaining a certain set of neutrino oscillation anomalies. Right. What exactly their phenomenological consequences are depends very strongly on their mass. So if they are light enough to participate in oscillations, which means that their mass has to be similar to the masses of the active neutrinos, then that's what they do. If they are heavy, then you would not see them oscillate because they would still mix with the active neutrinos, but any kind of oscillation would immediately decohere. Instead, in this case, the phenomenology is better described in terms of classical production and decay processes. So for instance, a neutrino hitting a target, producing a sterile neutrino, the sterile neutrino traveling for a while, and then decaying. Let's first talk about the case where sterile neutrinos participate in oscillations. In that case, the oscillation phenomenology stays formally exactly the same. So the derivation of the oscillation probability, where you start from an initial state, you write your flavor eigenstate as a superposition of mass eigenstates, you then time evolve it and project it onto the detected state. That's all exactly the same. Also the final result here for P alpha beta, that's exactly our main result for neutrino oscillations. The only difference now is that the mixing matrix is now not a 3x3 matrix, but maybe a 4x4 matrix, or, well, depending on the number of sterile neutrinos you introduce, it's going to be a larger matrix. But in the functional form stays exactly the same. So what would be the phenomenological consequences? Well, if a sterile neutrino participates in oscillations, then there is a chance that a fraction of the active neutrinos that we start with goes into that sterile state where it would be undetectable. So for instance, a typical experiment is you start with an intense mu-neutrino flux from pion decay, such as in an accelerator experiment or the upper atmosphere. This is a picture you've already seen. This is how the NUMI beam is produced. You see the protons from a particle accelerator hitting a target. You see the focusing system, the decay region in which the pions decay into neutrinos, and then finally the absorbing rock that filters out everything other than the neutrinos. And then you would look for missing mu-neutrinos. So you need a reasonably good prediction for how many mu-neutrinos you have produced, and then you compare the measured number to that number to see if any have disappeared. And what this plot shows is the rough sensitivity to such mu-neutrino disappearance. On the horizontal axis here, you have one of the elements of the mixing matrix, namely in this case the one that describes the mixing of the sterile state with the mu-neutrino. And on the vertical axis, you have delta m square. So that's now the delta m square between the mostly sterile mass eigenstate and the lightest of the mostly active mass eigenstates. And what you can roughly see is that these limits, they are somewhere on the order of u squared 10 to the minus 2, so that corresponds to mixing angles of 0.1, which means that essentially a 10% mixing between active neutrinos and sterile neutrinos is perfectly allowed by the data. What you can also see is that in this business, you typically get good results only if you combine various different approaches. For instance, here you have a set of different accelerator-based experiments, you have atmospheric neutrinos, and only if you combine those, you get a more or less a straight limit that covers a relatively large range in masses, because every experiment has its unique parameters and is sensitive in particular regions of the parameter space, but then the combination has a much broader sensitivity. So this field has for a while been driven very much by the fact that some experiments have observed anomalies that seemed consistent with oscillations involving sterile neutrinos. I would say much of that evidence has now, well, not completely gone away, but the picture looks much less consistent nowadays than it used to. So I don't think that sterile neutrinos are still a favored explanation for these oscillation anomalies, but I'm still going to use this opportunity to talk about the oscillation anomalies, because I think they can teach us important lessons, not necessarily about physics beyond the standard model, but maybe about physics within the standard model that is equally important. And I want to talk about two anomalies. The first one is called the gallium anomaly. The second one will be the so-called mini-Boon anomaly. So gallium anomaly. These are experiments with intense radioactive sources and with a radiochemical detection process. So radiochemical means you have a tank filled with some material. You wait for neutrinos to interact with that material, and then you chemically extract the interaction products. That's, in fact, a relatively old neutrino detection method. For instance, this is how the first solar neutrino experiments worked. And in fact, also these measurements came out of experiments that were originally designed for solar neutrinos. So, in particular, a useful element for that purpose is gallium-71. Gallium has the advantage that it's liquid at room temperature and that it has a neutrino capture cross-section with a sizable cross-section. Namely, gallium-71 plus an electron neutrino goes to germanium-71 plus an electron. And now the challenge in these experiments is you prepare your tank of gallium, you let it sit there for maybe a week or 2 weeks or 3 weeks, and during that time period, you produce maybe a few dozen germanium-71 atoms. And now the challenge is to extract these few germanium-71 atoms from maybe a few tons of gallium-71. So if ever there was a search for a needle in a haystack, this is it. And so if I naively tell you, well, they observed less germanium than they thought they should have produced, then you will say, well, of course, you've just missed some of the needles in your haystack. And it turns out it's not so simple because you can calibrate these experiments relatively well. And the way you do this is you deliberately inject germanium into them, you extract it, and you show that the amount you've extracted is the same as the amount you've put in. So the extraction efficiency has actually been demonstrated to be nearly 100%, maybe 90-something% or so. So it's generally believed that that method works. Still, they've observed a deficit. This is shown here on the right-hand side for 4 runs of 2 older experiments, Galex and Sage. Galex was an experiment in the Gran Sasso laboratory. Sage was an experiment in Baksan in the Caucasus in the Soviet Union. If everything was normal, you would expect these data points to cluster somewhere around 1. So the measured neutrino interaction rate being equal to the predicted interaction rate. But in fact, what you observe is that on average you observe fewer than you should, and the statistical significance of those 4 data points combined is somewhere close to 3 sigma. I should also talk about the sources. I said here these were experiments done with intense radioactive sources. So that means you have some material, for instance chromium, you bring it into a nuclear reactor where you irradiate it with neutrons, thereby activating it. And then you take it out of the nuclear reactor, you bring it to your neutrino detector, you place it somewhere close to the neutrino detector, and this thing is now extremely radioactive, so we are talking about megacurie sources here. And because it's so highly radioactive, it produces lots of neutrinos, and because it's really close to your neutrino detector, you're going to catch some of those. Now originally, these experiments were actually meant to demonstrate that the neutrino detectors work, because the primary goal of these detectors was seeing solar neutrinos. So by using these human-made sources, they wanted to show that in fact the experimental technique works. Nowadays it's more or less the opposite way. We think we understand solar neutrinos very well, and the solar neutrinos provide the calibration, and this is the measurement. Anyway, there is this deficit that has been unexplained for a few decades. So the question arises, could this be explained by electron-neutrino disappearance into a sterile state? If you look at the numbers here, you'd need quite substantial disappearance. You'd need maybe 10 to 20% of your neutrinos to disappear into a sterile state. That is, so for a while that used to be okay. Nowadays it is probably in conflict with observations from reactor neutrinos, which would then also disappear in the same way. So naively one would say, oh, okay, who knows what's going on there? Let's forget about it. But the problem is this has recently been confirmed, and it's no longer at 3 sigma, it's almost at 5 sigma. The way it's been confirmed is again by an experiment which has the very modest name BEST. It stands for the Baksan experiment on sterile transitions. So it's once again located in the Caucasus Mountains in Baksan. It's once again based on this neutrino interaction with gallium, so you can argue that the systematic uncertainties of this new experiment are certainly not completely uncorrelated with those of the old experiments. The advantage this time is there is now 2 volumes of gallium. The hope was that they would see a different amount of disappearance in the 2 volumes, maybe giving a first hint that there's actually an oscillatory pattern. Well, they did not see that, but they saw a significant deficit, so this stands now at almost 5 sigma. And yeah, people have thought about lots of explanations. No one has really come up with a good explanation beyond the standard model. People have come up with a lot of interesting explanations within the standard model, but all of them have been refuted. For instance, one hypothesis that caused some stir recently is, so this cross-section, neutrino capture on gallium. Well, it's a nuclear reaction, so obviously we can't make first principles predictions for the cross-section. But you need a cross-section, because how can you measure a neutrino flux if you don't know what your cross-section is? But the thing is, the inverse process, germanium-71 decay to gallium-71, that's a well-studied nuclear decay. So from the measurement of germanium-71 decay, you can extract the nuclear matrix element of this process, and then you just change the kinematic factors appropriately, and you get a very good prediction for this cross-section. So there have been some people who were arguing that, well, this measurement of germanium-71 decay, that's already decades old, maybe there's something wrong with this measurement, but no, turns out this measurement is perfectly fine. It has been confirmed by multiple groups now, so that was not it. But yeah, it's fun to think about it, but so far no one has come up with anything that resembles any kind of convincing explanation. Okay, the other anomaly I wanted to talk about is from an experiment called Mini-Boon. That's an accelerator-based experiment. So that picture here is again how you make a neutrino beam in a particle accelerator. It's exactly the same principle as in the previous picture, but because it was drawn by a different experimental collaboration, it just graphically looks different. You have again protons from a particle accelerator. In this case, this is the booster at Fermilab. They are dumped onto a target. The resulting pions pass through a magnetic focusing horn to form a nice forwardly oriented beam. The pions are allowed to decay, and then there's rock that gets rid of everything other than the neutrinos in the beam. And finally, there's a detector, which in this case is a liquid scintillator detector. So what Microboon has observed is shown in the plot on the bottom left. The horizontal axis is the neutrino energy, the vertical axis is the number of events. So you see there is a number of backgrounds here, so it's definitely not a background-free measurement, but you also see that the data points are far above the background. And that is again a statistical significance of almost 5 sigma, 4.8 sigma or so. And the channel they've been looking at is muon neutrino to electron neutrino conversion. So you may say, okay, well, this is a process we also have in the standard model. But the thing is, this experiment was relatively close to the neutrino source. And we know the standard oscillation parameters well enough to say that over such short distances, oscillations in the standard model would not have had time to develop. So if these transitions were to happen over such short distances, the only possibility to do this via oscillations would be that there is a new neutrino state involved. It's not entirely correct to say that this is muon neutrino to sterile neutrino to electron neutrino oscillations, but this analogy still gets you relatively far. The presence of a sterile neutrino with a somewhat larger mass than the active neutrinos could have this effect on oscillations. So it could mediate oscillations from muon neutrinos to electron neutrinos even over short distances. Well, the right-hand side is just a parameter fit. Horizontal axis is the mixing angle between active and sterile neutrinos. Vertical axis is delta m square. So you see that we're roughly talking about sterile neutrinos with a mass of order 1 electron volt here, so maybe an order of magnitude above the active neutrino masses. Now, in principle, sterile neutrinos are a perfectly good explanation for the Mini-Boon anomaly. The problem is they have not been confirmed by other experiments that should have been sensitive as well. And that's why it's paramount to think about standard model processes that could explain the Mini-Boon anomaly. I think it is a highly significant anomaly, so we better figure out what it's about. And if it's not new physics, but misunderstood standard model physics, then it's probably also good to learn about this before we run the next generation of experiments where we might make the same mistake again. So I'm using this opportunity to highlight a little bit the difficulties associated with making predictions for neutrino oscillation experiments, making background predictions, calculating cross-sections. So let's focus on, among these many background contributions here, let's focus on one particular contribution, namely the one shown in light brown here. And in the legend, they label this the delta to gamma n background. So what is that? Remember that what you have in this experiment is you have a very large flux of muon neutrinos passing through, and what you're looking for is a small signal of electron neutrinos. But of course the muon neutrinos sometimes interact as well, and in most cases you're perfectly able to distinguish those interactions from an electron neutrino interaction because there's a muon involved, and muons are easy to see. But look at the process written up there. Imagine a neutrino, like a muon neutrino, comes in and undergoes neutral current scattering on a nucleon. And in this neutral current scattering, the nucleon is excited. The lowest lying excitation of a nucleon is the delta 1232 resonance. So let's assume that this excitation happens. So neutrino plus nucleon goes to neutrino plus a delta resonance. Most of the time, the delta resonance decays back to a nucleon by emitting a pion. Pions are visible to Mini-Boon. So that background can be efficiently rejected. However, there is a rare decay through which the delta resonance decays radiatively by emitting a photon. The branching ratio for that decay is somewhere at the few times 10 to the minus 3 level, so few per mil. And the thing is that in miniboon and in many other detectors, it's very difficult or impossible to distinguish photons from electrons. Both particles produce an electromagnetic shower in the detector. And because it's neutrino-induced, that electromagnetic shower appears to come out of nowhere. So the only signature you have is an electromagnetic shower coming out of nowhere, starting somewhere in your detector. And you cannot tell whether this was initiated by a photon or an electron. So a single electron, that's the hallmark signature of a charged current electron-neutrino interaction. A single photon, well, that's for instance a signature of that background, and they look exactly the same to an experiment like miniboon. So therefore, this is a potentially dangerous background. So obviously, it has been studied in great detail. Since it's hard to predict because this excitation of a nucleon to a delta resonance, well, it's a hadronic process, there are large uncertainties associated with it, so it's probably better to measure it. And in fact, it can be measured because the dominant decay of the delta is to a pion. So by looking for those pions, we can in principle get a handle on the delta production rate in miniboon. So that sounds simple, but in the end, nuclear physics gets you anyway. And the reason is that this process typically does not happen in vacuum, but it happens inside an atomic nucleus, for instance, inside a carbon nucleus. So after you've produced your delta resonance and it has decayed, the decay products still need to make their way out of the nucleus. And this can affect you in two ways. First, if that pion interacts with another nucleon, it may excite this nucleon to a second delta resonance. So now you have in your event not one delta resonance, but two delta resonances. So this means that the chance that at least one of them undergoes this rare radiative decay is enhanced. The other possibility is that the pion is simply absorbed. So in this case, your control measurement of delta 2 pi n would be suppressed. So in both cases, your data-driven background estimate would be biased. Obviously, the experimentalists are aware of this and are taking this into account in their analysis. But of course, still, even though it's a data-driven analysis, this is the point where nuclear modeling comes in, potentially introducing uncertainties. Now it has been studied at great length whether these uncertainties could be large enough to explain the anomaly. The answer is no. Also by now we have measurements from detectors that can actually distinguish photons from electrons. They do not see an anomalous excess of photons, so that is probably not the explanation for the miniboon anomaly. But still, I think it shows nicely what the complications are that we have to deal with when we talk about neutrino interactions. So more broadly speaking, what I've just said, this kind of difficulty affects not only explanations of obscure anomalies, but this also affects the flagship measurements of neutrino physics. Anytime you do something with neutrinos, you need to detect them, so you need a reliable prediction of their cross-section, and there are no reliable predictions for neutrino cross-sections. And so in a sense, we are running neutrino experiments in a way that's similar to running the LHC without really knowing parton distribution functions. And the reason we are in that situation is because, well, it's a very complicated process and one that I think requires, on the one hand, some experimental work, but that especially requires substantial theoretical work. So why are neutrino cross-sections so complicated? First, neutrinos, the nucleons on which neutrinos interact are not on their own. So they are embedded in a nucleus. So this means rather than just having to study an interaction on a free nucleon, you need to take into account, for instance, the nuclear initial state. So the nucleon that you're scattering on is in some bound state inside a nucleus. And that obviously affects its kinematics. In particular, it's coming in with some initial state momentum that is poorly known. Second, that nucleon is not on its own. There's lots of nucleons around it, and they are very strongly bound to each other. So there is a large probability that while the neutrino interaction is going on, the nucleon that has been struck exchanges a pion with another nucleon. So in that sense, the neutrino effectively feels the presence not only of one nucleon, but also of a second nucleon. And finally, even after the interaction is over, the interaction products still need to make their way out of the nucleus, possibly interacting with other nucleons. So that's a final state interaction cascade. Now, even the process, the hard process, so the interaction with a single nucleon, even that is non-trivial already. For instance, if you are at relatively low energies, meaning well below a GeV, then that process is just quasi-elastic scattering. So that means the momentum transfer is small enough that the neutrino sees the nucleon as a single entity, is not able to resolve its substructure. So then we still need to worry about form factors, but okay. At somewhat higher energies, around a GeV, we are in this regime where we can excite nucleon resonances, for instance, the delta resonance. And there's not only the delta, right? At around a GeV, there's all kinds of hadronic states that you can in principle excite. So a very, very messy energy range to sit in, but luckily that's the energy range where neutrino oscillation experiments operate. And finally, at higher energies, the scattering is deep inelastic. That's again a region that's under somewhat better theoretical control. Well, then in between, you have the energy range where these two particle to hole processes, so the scattering on two nucleons is important. Okay, so this was basically just to show you where the complications are. I don't have good solutions to these complications, but it has recently become a very active field of research. So if you have good ideas on how to make progress in this field, thousands of experimentalists will love you, will absolutely adore you. Okay, questions on this topic, on neutrino-nucleus interactions, on sterile neutrinos in oscillation experiments, on oscillation anomalies? Yeah.
I mean, it's not related to probabilities, but
Yeah.
if there were actually sterile neutrinos, can we do something in cosmology, for instance, from the effective number of relativistic?
Yes, we can. So that's an additional problem. If you had sterile neutrinos that are light enough to participate in oscillation experiments, then at least in the minimal models, they would immediately be ruled out by cosmology because they would be produced cosmologically, they would contribute to N effective, they would contribute to the sum of neutrino masses, and the universe would look very different. Now, there are mechanisms of hiding sterile neutrinos from cosmology. The way this typically works is by preventing their production in the early universe. So if you suppress their production until sufficiently late times, then you can avoid some of the cosmological constraints. It's in principle possible, but it requires typically then extra additions to the model.
Because to explain this oscillation anomaly, you should assume that they're very light.
Yeah, so then you need to hide them from cosmology, which typically requires the sterile neutrinos to have, for instance, some interactions among themselves or so. That's one way of hiding them from cosmology, at least to some extent. Okay, then let's switch gears once again and talk about sterile neutrinos as a dark matter candidate, and we're going to do that again on the blackboard. And because I have my notes on this, not in paper form but only on the computer, I will have to run back and forth between the blackboard and my computer a couple of times. Okay, so let's call this 3 sterile neutrinos as a dark matter candidate. Sterile neutrino dark matter. So the idea here is, well, a sterile neutrino is a neutral particle. It's electrically neutral, so that satisfies one important property of dark matter. And if it's not too light, then it can be cold enough that it can actually be cold dark matter. So in that sense, a neutrino is perhaps a natural dark matter candidate. Of course, it's not completely isolated. It still talks to the standard model through, once again, the neutrino portal. So, so imagine we have a sterile neutrino nu s coupled via the neutrino portal. So we have some U-cover coupling, L bar, H twiddle, nu S. Then, if that's the only way the sterile neutrino talks to the standard model, in order to make this a successful dark matter candidate, we need a coupling here that is large enough to produce the sterile neutrinos in the early universe, but at the same time, small enough for them not to have decayed yet. Because obviously through that interaction, the sterile neutrino has a way of decaying, and that decay should be sufficiently slow so that the dark matter is still around. So production and decay via this coupling. So let's first talk about how the production works. The idea here is, so you start with a population of only active neutrinos. So unlike in WIMP models, where you assume you have a thermal population of sterile of dark matter from the start, here you don't have that. The assumption is, since this is the only coupling of sterile neutrinos to the standard model, that coupling is too small to ever bring the sterile neutrinos into thermal equilibrium. So the idea is you start with a zero abundance, and then you slowly produce some of them through this coupling. Now, how does this work? The intuitive picture is, so let's call this 3.1, nu S production. So the intuitive picture is, you start with a population of only active neutrinos. So start with only nu A active neutrinos. Those active neutrinos will immediately start oscillating. So after a while, you have produced a small abundance of sterile neutrinos. The oscillation amplitude, as you know, is sine squared 2 times the mixing angle, and because we need to average over those oscillations, this means the abundance of sterile neutrinos that has been produced after a while is 1/2 sine squared 2 theta. So oscillations convert a fraction of about 1/2 sine squared 2 theta of nu A to nu S. And this theta here, so by theta I mean the active sterile mixing angle. So the nu A, nu S mixing angle. But now the early universe is hot and dense, so neutrinos cannot oscillate completely freely. From time to time, the neutrinos will interact. The interactions they undergo are mostly charged current interactions, and charged current interactions are flavor sensitive. So in a sense, every time the neutrino interacts, its flavor is being measured. So that means its wave function, which before the scattering is in a superposition of active and sterile state, collapses into either the active neutrino or the sterile neutrino state. So at a CC interaction, collapses the wave function to either nu A or nu S. But what this means is that after the interaction, I now have clearly separated my remaining active neutrino population and my small fraction of order 1/2 sine squared 2 theta of sterile neutrinos. And now the active neutrinos start oscillating again. So the nu A start oscillating again. And the next interaction produces again a small fraction of sterile neutrinos. So the next interaction produces again a small fraction namely a fraction proportional to 1/2 sine squared 2 theta of nu s. And then the process repeats. So that means every time the neutrino interacts, you produce a little more sterileness and you reduce a little bit the activeness of your neutrino state. In principle, of course, there's also a back reaction, so of course also the sterile neutrinos start oscillating, recreating a little bit of active neutrinos. But as long as the sterile neutrino abundance is way, way, way below the active neutrino abundance, that is a totally negligible process. So this back reaction is totally negligible. So the net effect is always that you slowly increase the abundance of sterile neutrinos. And this mechanism is called the Dodelson-Wittrow mechanism. Okay, now let's do this more formally. We start with the Boltzmann equation. So many processes in the early universe are described by a Boltzmann equation, and this one is no exception. So as you know, the Boltzmann equation is an equation that describes the time evolution of a distribution function. So in this case, the Boltzmann equation reads as follows. It's a partial derivative, d over dt, minus h e times the sterile neutrino distribution function, which is a function of e and t. And we set this equal to 1/2 sine square 2 theta times an interaction rate gamma times the distribution function of active neutrinos. So that's also a function of E and T. So this is the nu s phase space distribution. This is the active neutrino distribution. This is the interaction rate. Well, and we've already talked about the mixing angle. And in principle, of course, we need to take into account matter effects here. So this theta is the mixing angle in matter, but I'm going to skip over this here. The sterile neutrino distribution, oh, and I forgot an important derivative here. So this is not just Hubble times E, this is Hubble times E times D over dE. So H is the Hubble parameter. The active neutrino distribution can be taken to be simply a thermal distribution. So we take this to be Fa is 1 divided by e to the minus e over t minus 1, because it's a Fermi-Dirac distribution, and I think I need an e square in the numerator to get the units right. In the end, no, I don't even need an e square in the numerator. So just 1 over, and there should also not be a minus sign here because it's already in the denominator. And it should be a plus because it's a Fermi-Dirac. So that's just the Fermi-Dirac distribution. And Fs, that's the quantity that we want to solve for. Now, what's written here on the left, so the shape here on the right-hand side, that's essentially, by the arguments given over there, the production rate of sterile neutrinos in a short time interval dt. And what's written here on the left-hand side is just the total time derivative of Fs, so d over dt, Fs of E, comma t, can be written as the partial time derivative of Fs, E, comma t, plus the derivative of Fs with respect to E multiplied by dE over dt. And dE over dt if you have a particle that's just propagating freely, then the only thing that affects its energy in a time-dependent manner is redshift. Namely, as the universe expands, the particle, the energy gets smaller. So let's write the energy as some sort of E0 times a to the minus 1 divided by dt. So I'm just explicitly writing out here the dependence of the energy on the scale factor of the universe. So that the E0, that's the, in a sense, let's call it the co-moving energy that can be pulled out of the time derivative. Now the d over dt acting on a to the minus 1, that gives a minus a to the minus 2 times a dot. Now a dot over a is just Hubble. So that's the Hubble parameter times E0 a to the minus 1. And E0 a to the minus 1 was just E. So this gives the minus h times E. So this explains the two terms here on the left-hand side. It's really just the total time derivative of the sterile neutrino distribution function coming on the one hand from the actual change in, say, the number density, and second coming from the evolution of the energy, which slowly shifts particles from higher energy bins to lower energy bins. Okay. Now to solve this equation. As Yvonne has argued in her lecture, we are typically not interested in the full energy dependence of the distribution function, but what we are mostly interested in is the number density. So the quantity that we are mostly interested in the sterile neutrino number density, which is given by 2 times integral d3p. Let me see if I need a factor of 2 pi cube here in my conventions. Yes, I do. 2 pi cube times Fs of E comma t. So that's just the sterile neutrino number density. And that is now just a function of time. Energy has been integrated over. So as we do this, it is moreover convenient to go from derivatives with respect to time to derivatives with respect to A. So it is convenient to go from d over dt to d over dA. So, for instance, if we want the time evolution of this number density, and we write this not as an evolution with time, but as an evolution with A, then, well, we plug in this expression. So this is 2 times d over dA integral e square times dE. So I'm already carrying out the angular integrals here, divided by 2 pi square. So the factor 4 pi from the angular integrals cancels against some of the factors in the denominator, times Fs of E comma t. And I've set energy and momentum equal here because all of this is happening at a time when all our neutrinos are still highly relativistic. Okay. So now, this derivative in A, it can act either on the function fs under the integral, or it can act on the prefactors of E here. So let's first consider the term where it acts on fs. So that yields a 2 times, I leave some space here because I want to pull one factor out in a moment, e squared dE divided by 2 pi square. Now I'm first considering the term with the partial time derivative, so partial d over dt fs of e comma t. And now I still need dt over dA, which means that I basically need a 1 over a dot. Then the second term is the one where the dE dA acts on the energy appearing inside the argument of the fs. So plus 2 times integral e squared dE over 2 pi square times d over dE fs of e comma t. And what I now still need is a dE over dA. And that is something I have in a sense already derived here. Let me quickly say it again. So dE over dA. I again write E as E0 a to the minus 1. If I take the derivative with respect to A, this gives me a minus E0 divided by A squared, which is a minus E over A. So I'm going to include a factor minus E over A here from dE over dA. Okay, and now finally I need to include the term where the derivative with respect to A acts on the prefactors here, the E square and the dE. Those are all energies, so the dependence is always the same. So I get a factor of 6 because there's 3 such factors, one factor of E square and one factor of E. So I have a 6 times integral E square dE divided by 2 pi square times A, so 1 over A. I also get a minus sign in the same way as here, and the fs of E comma t is unaffected this time. Okay, if I want, I can still massage this a little bit by multiplying it from the left-hand side with A dot and then replacing A dot by the Hubble parameter and so on. So if I just multiply the above equation by A dot from the left, I get dA dot times dNs over dA is equal to, so here the A dot cancels. So that gives me just a 2 times integral E square dE over 2 pi square times d over dt of Fs. In the second term here, I have an A dot over A, which is a Hubble parameter. So minus 2 times h times integral integral E cube dE over 2 pi square times d over dE of Fs of E comma t. And the third term here, that's again, I have again an A dot over A, so that's again a Hubble parameter, so minus 6 h times times just the integral E square dE over 2 pi square times Fs, and this is just Ns. So minus 6 times h times Ns of t. Okay, oh, and I lost a factor of 2. There's still this factor of 2, so this should not be a 6, this should be a 3. Yeah? Was that about the factor of 6 or about something else? Okay, yeah. I had omitted this factor of 2. If I take this into account, it's just a minus 3 here. Okay. So, now with these results, I can rewrite my Boltzmann equation in terms of an equation for Ns. So this means the Boltzmann equation can be rewritten in the following form. So we have here just this A dot dNs of t over dA. And now when I look at this, I have here let's see, all of this collapses into a plus 3h ns. So let's see, we take from over here this d over dt minus he d over de. That's exactly the integrants of the first two terms here, so of this term and this term. So the only thing I need to compensate for is this minus 3h ns here. I need to add this back in, right? So what I have on the left-hand side of my Boltzmann equation is the first two terms on the right-hand side here, integrated over momenta. So by this equation here, I can equal them to a dot dns over dA plus 3h ns brought to the other side of the equation. So that means the left-hand side of the Boltzmann equation has been in a somewhat simplified now. And the right-hand side, well, on the right-hand side, I essentially get an integral. So I'm going to absorb this into a new definition. So I'm going to call this little gamma, where little gamma is now given by, let me make sure I get the prefactors correct, but it's basically the momentum integral over the collision term here. So it's 1 over NA times integral d3p over 2 pi cube times sine squared 2 theta times gamma, and I still need I still need the distribution function, so times a 1 over e to the e over t plus 1. So that's the term that now contains all the particle physics, like especially the interaction rate. Okay, so that's in principle a useful result. It's now a differential equation in just one parameter. So that's an equation that one can in principle solve, and then one finds indeed this slow freeze-in of the sterile neutrinos. It can be massaged a little more. I think I'm not going to do this here because this is going to be in the notes which we are going to upload shortly. If you write this equation now, not in terms of NS and NA, but in terms of the ratio of the two, then it becomes even simpler, but there's not much additional physics in it. This is essentially the equation that you can solve. If you look at this in terms of this ratio, then what mainly happens is that this term here, which describes just Hubble expansion, drops out because Hubble expansion affects active and sterile neutrinos in the same way. Right, so once again, we have three terms here. The term on the left-hand side is the time derivative of the sterile neutrinos. That's what we are interested in. There's one term that takes into account the trivial time dependence of the number density due to Hubble expansion. And there's one term that takes into account the actual creation of sterile neutrinos via interactions. So that's how sterile neutrinos are made in the early universe. Okay, questions up to this point? Yeah.
Just I didn't follow where the 3 factor came from.
This one here. So I have to apply. The derivative to the two factors of e and to the dE. There's like 3 factors that can in principle be a factor, so that gives this extra factor of 3. Okay, so that's about sterile neutrino production. So as I already said before, this interaction through which the sterile neutrinos are made, namely the mixing with the active neutrinos, that can in principle also lead to their decay. So sterile neutrino decay. So the first possibility is that through the mixing with the active neutrinos, the sterile neutrino can talk to the Z boson. So there is in principle a process where you start from a new S that mixes into a new A, and then through the exchange of a Z boson, it goes to an active neutrino bar, and over here there's also an active neutrino. So a sterile neutrino going to 3 active neutrinos. That process is clearly not observable because there's only neutrinos in the final state. It would in principle be dangerous if the sterile neutrino mixing angle was so large that the majority of the sterile neutrinos would have decayed already, because that would mean going from a more or less non-relativistic dark matter particle to ultra-relativistic standard model particles. So if that happened on the time scales of the age of the universe, it would have affected structure formation. Remember that there's a very strong preference for cold dark matter over hot dark matter. So if this process was happening too fast, the sterile neutrinos would effectively contribute as hot dark matter, and that would be ruled out. The constraint that imposes is mostly that the sterile neutrinos should not be too heavy, because so if you look at the rate for this process, so gamma for nu s to 3 nu a, by very rough dimensional analysis, there's a factor of G Fermi squared here because there's a Z boson involved. And then to get the dimensions of a rate, it needs to be multiplied by 5 powers of the typical energy scale of the process. The only scale available is the sterile neutrino mass. So that goes as ms to the 5th power. So if the sterile neutrinos are made heavier, then very quickly this rate becomes large. And because this would be phenomenologically unviable, this imposes the constraint that sterile neutrino dark matter should typically not be heavier than a few keV. So to make sure our dark matter hasn't decayed yet, we need to require that ms is somewhere less than 10 keV. That's totally not legible here. Less than 10 keV. On the other hand, you also don't want to make it too light, because if it was too light, then the sterile neutrinos themselves would be too hot. And if you make them even lighter, at some point you would run into what's called the Tremaine gun bound, which is essentially a constraint on from Pauli blocking. So there are regions in the universe where we know that the dark matter density is fairly high, for instance the center of our galaxy, but since this dark matter candidate is fermionic, if you make it too light, then to account for the observed dark matter mass density in these dense regions, you would need to pack them very tightly, and because they are fermions, that's forbidden. So that imposes a lower limit. Let me make a brief comment on this. So a lower limit on ms is imposed by Pauli blocking in dense regions like the galactic center. Okay, but if we are within these constraints, then in principle, at least from this perspective, sterile neutrinos remain a viable dark matter candidate. But now there are extra decay modes that we also need to worry about, and these are radiative decays. In particular, you can have a process where a sterile neutrino, through mixing with an active neutrino, talks to a W boson and a charged lepton, and radiates a photon. Of course, you can equivalently also radiate the photon from the charged lepton line. So there is a similar diagram where the photon is radiated from down here. Here's the W, here's the charged lepton, here's the sterile neutrino, here's the active neutrino. So that process is, in terms of the rate, it's suppressed compared to the 3 neutrino decay because there's an extra loop. But on the other hand, it has a very nice observable final state, namely a monochromatic photon. And monochromatic photons are something you don't get every day in astrophysics. So in that sense, it's a pretty neat signature. The exact expression for this decay rate is going to be in the notes. It's again proportional to the Fermi constant squared and to the mass to the 5th power. So very roughly, it's proportional to Fermi squared mass to the 5th power. There has to be an alpha electromagnetic. Well, and then there's order 1 factors from the fact that it's a loop diagram and so on. So it's a little bit suppressed, but that suppression is way overcompensated by the fact that this is a visible final state. So this leads to monochromatic photons. And if we look at these mass constraints, less than 10 keV, but heavier than maybe 1 keV or so, then these are photons in the X-ray range. So this predicts monochromatic X-ray lines. And that's a very characteristic astrophysical signature, because there aren't that many things that give you monochromatic X-ray lines. There is admittedly X-rays from atomic physics or from atomic transitions in standard model atoms, but those we understand reasonably well. So by looking for a monochromatic X-ray line that is not in any of those places where we expect X-ray lines to be based on atomic physics, then that's a very characteristic signature, and in fact that imposes extremely strong limits on sterile neutrino dark matter. And that's the final thing I'm going to do. Let me see if the projector comes on quickly. I'm going to show you the diagram on the projector, otherwise I'm going to draw it. Come on, come on, come on. Wait. Here we go. So if you look at this diagram, then you have on the horizontal axis the sterile neutrino mass, on the vertical axis the sine square of twice the mixing angle. So you see that the masses that we are talking about are indeed of order few keV to few tens of keV, and the mixing angles, on the other hand, are very small, because if they were too large, then obviously the sterile neutrinos would have decayed already. And all these colored regions coming down from the top, these are constraints from these monochromatic X-ray searches. The white region is essentially the parameter space that is still ruled out from the point of view of these searches. So you see that the parameter space there is not too large. And in fact, what's not on this plot is the line along which the Dodelson-Wittrow mechanism would give you the correct Rayleigh abundance, and almost all of that line is by now ruled out. So this means that the simple Dodelson-Wittrow mechanism, the way I've presented it here, is no longer a completely viable mechanism for sterile neutrino production. There are, however, extensions that still work. For instance, one of them is called the, now what's it called, the mechanism where you have a lepton asymmetry, Schiff-Fuller mechanism. It works in the same way, but taking into account matter effects in a universe that has a somewhat larger lepton asymmetry than the baryon asymmetry. So we have a measurement of the baryon asymmetry of the universe, but in principle the lepton asymmetry of the universe could be larger. And especially because we don't understand how baryogenesis happened, that is certainly a possibility. So in that case, you can have your production rate enhanced via the MSW effect, and in this case, sterile neutrino production is still viable. Other scenarios that are viable include those where the sterile neutrino is produced in the decays of some heavier particles rather than just through the mixing. But it's nice to see how this is really a testable dark matter scenario, where at least in the minimal scenario, almost all of the viable parameter space has already been ruled out. It's been constrained from multiple directions. So in that sense, it's phenomenologically quite nice. What you can also see there is this data point with the error bar in the upper left-hand corner of the plot. There was for a while, or well, there actually still is, an unexplained X-ray line that has been observed in some of these data sets. And for a while, some people have very strongly advocated for explanations of this X-ray line in terms of sterile neutrino dark matter. I think by now this explanation is again no longer perfect, mostly because this extra line has been seen in many different regions of the sky, so in many different astrophysical regions, and the relative strengths of those signals in the different regions does not really match the relative dark matter abundances that you would expect. So most likely that line is due to poorly understood atomic physics, but still. Okay, so this brings me to the end of what I wanted to show you today. I'm of course happy to answer further questions, and I'd like to thank you for your attention throughout the week. Oh, sorry. Sorry?
What's the name of the other mechanism you're talking about?
Shea-Fuller mechanism. Shea with S-H-I and Fuller with F-U-L-L-R, L-L-E-R.
So I
Yeah.
was wondering about the interaction term that was written in the Boltzmann equation. So that does that correspond to the Feynman diagram that you drew?
No, that corresponds to it corresponds to a normal charge current interaction on a standard model particle. So the diagrams I've drawn here, these are diagrams for the neutrino decay. So this gamma appearing in my Boltzmann equation, that is charged current scattering or neutral current scattering on standard model particles though. Yeah?
So in these X-ray satellites, what is the altitude of the satellites? Does it provide an enhancement for the detection? Because I can see that there might be some interference with the magnetic field of the Earth, maybe even though it's very small.
Why would the magnetic field affect the X-ray detection?
Some electromagnetic interactions, the loop corrections. Maybe like Chandra might...
Oh, you're thinking about the sterile neutrino affecting... The thing is that in here locally the dark matter density is probably too low that we can see anything. So the way we can see this is really by looking at regions where there is a lot of dark matter in a relatively small region of the sky. So I don't think that local effects play a role here. You're really seeing signals from maybe a dwarf galaxy or a distant galaxy cluster or so, where you see the integrated signal over the whole galaxy cluster, for instance. So I think the local population of dark matter, that signal is too small to be observable.